I think we covered this part on the board, actually. Remember how we were going from, we know what the loop invariant is, but we don't know what the code is, right? And so we try to use the proof for the loop invariant to get the code, right? Did people understand that? All right, so when I was covering that yesterday, there was a surprisingly long conversation. Well, surprising to me, right? This is an example where things seem so obvious to me, but we had a long discussion about it, right? And so I made more slides on the way home. And so I think somebody should always see my new slides. So here's another case, right? We're trying to get the post condition from the loop invariant in the exit condition, right? But the concern people were having was, how do you come up with the exit condition, right? And then how do you get the code for the exit? I'm not really sure what they didn't understand. Maybe you can help me here, because it all seems so straightforward to me. But anyway, let's look at these new slides. All right, so this is saying, again, we know the loop invariant, right? Maybe we don't know the exit condition, right? Maybe we don't know the code at the end. All right, so what's our post condition? Our post condition's that. Now what we're trying to do is we're trying to match these up, right? And to me it says, look it, how do you match them up? When is this true, right? What do we need? Well, we need the s's to be the same, and we need the i's to be the same, right? Does that make sense? And all right, and now we say, well, then I was thinking, well, how do I know which of these is going to be the exit condition and which is going to be the code, right? I don't know. Is it obvious? Here, I is the measure of progress, right? So I is changing, and at some point I will equal I, right? So it just seems to me straightforward that I should be the exit condition, right? And then what about this guy? Well, we don't know S. S is our output, right? In fact, the post condition is somewhat S is returned. So it seems to me that should be the final code. Right? People following this? All right, so again, I'm sort of differentiating between math statements and code. Right? So where do these math statements kind of go? Now let's try to translate the math statement back to code and see what we get. All right, so here's our code. These. Maybe I should get rid of these, because our code's up there. I was like, that's not part of our code. No, our code's up there, right? So the question is, right, this exit condition, what do we know about it? It's like when we fall out of the loop, when does this apply? This falls when I fall out of the loop. I'm going to put an insertion here. And what do I want to be true when I fall out of the loop? Right? I want the loop invariant to be true, but what do I want to be true here? I need the exit condition to be there, right? That's where we want it to be true. And so then how do we get it to be true, right? What code makes this math statement true? Well, we stick in the code that we exit when they're equal, and so then when you exit, you drop down here and they're equal, right? And but then, the little scary man says he likes while statements. He doesn't like exit conditions, right? So then, in general, the while statement is the negation of the exit condition, right? I do it while, and I stop when the exit condition's true, right? So we could have that be the exit condition, right? People like that as an exit condition, right? Well, it makes this guy a little nervous. It makes me a little nervous because, right, I know that I is an integer, right? So I'm going to hit capital I. But maybe somebody will come through and change my code. Maybe capital I, oh, that's supposed to be a little I, right? Maybe a little I will skip capital I. People following me? So that kind of code makes me nervous. So you make it a little safer by doing this, right? And then I still say this stuff is a little scary, right? We need to sort of convince ourselves. You still need to do some arguments that, well, little I is an integer. Why when this drops out, we're going to have this, right? You have to say, well, it's an integer and it's only increasing by 1, and so when it's bigger, it's going to be bigger by 1, right? Everybody got that? All right, so here's my question. So let's keep going. Now we need to know what code do we put in there, right? Now we get the post condition, and here's our math statement, right? So what's the code do we put in? Do we put little s equals capital S like this? No, you got to switch them, right? Everybody happy? Now, was this self-evidently obvious, or was this worth doing? People felt it was worth doing? Yeah? Here? Here. Oh, because when we were developing the post condition, when we had loop invariant plus not x, but plus x condition in code gives me post condition, we decided that this was something that we needed, right? This was our math statement. And then I needed to convert the math statement into code. Now, the other way you can look at it is right, so here's where we're trying to prove that these things give us a post condition, right? And so we figured out, this is the loop invariant, we figured out that the x condition is I equals capital I, right? And then what does that give us? That gives us little s as our answer. No, but our post condition is capital S as our answer. And that's why in the code, you have to set them to be equal. Does that answer your question? Is everybody, that was good? That was all right? Uh-huh. Yeah. Yes. All right. Oh, all right. Well, maybe, and sometimes, when I try to explain things with more pages, it only makes it worse, right? So we'll have to just see whether I'm confusing him or helping him, right? Instead of little s and big S? The reason I use it is to give you a hint that they're really going to be the same. They have the same sort of meaning. We could use a prime, but then we often use prime for going around. I don't know. Anyway, we haven't actually answered his question yet, so hold them all, right? His question, well, let me tell you what I did here, right? I was trying to say I don't know the codes yet. I don't know the exit condition yet, right? So I'm trying to fill things in here. Let's go back even further. Right here, right? Here I don't know them. So then I say so we're focusing and we need to get the post condition. We need loop invariant plus what gives me post condition. It's kind of like x plus y, 3 plus what gives me 7. Well, the what's going to be a 4. So here's, right? So now I'm working on the what. And I'm getting the what in math language, right? So in math language, what I see is I need these two to be equal. And I need these to be equal. I to be equal. So I put those down in math. Now, why did I put it little s equals big S? Well, because I was going to messing with you, right? I know that eventually it's going to go the other direction, right? But I wanted there to be a little difference between my math and my code. And here I'm just thinking, what do I need? I need them to be equal. So here's a math statement. We're good. So we can certainly see we have a proof here, right? We have a proof that if the loop invariant's true and these math statements are true, then we get our post-condition. Right? Does that make sense? So if I'm focusing on, I don't know, not loop invariant here. Yeah, I mean here, loop invariant post-condition. We're focusing on the proof. Right? What do we need from the proof from here? We need these two things. Right? And maybe in this easy example, it just seems so easy, but I can imagine a harder problem where you don't know what the exit condition is. You don't know what the code should be. And so you should think loop invariant plus what facts are going to give me the post-condition. Right? And these clearly are the facts. Right? And now we can work on from the math, how do we get the code? Right? And so then I was saying, well, where did it, I guess the first part that was tricky is which of these facts are going to be from the exit condition, right? And which of these facts are going to be from the code. So I had to sort of think, remember what my actions are, right? I do know the actions. So I can think I'm rolling the actions forward, right? What happens in the action? If you recall, little I keeps getting bigger. Little I was my measure of progress. Little I gets bigger. So what's my exit condition? Well, I need this to make the proof. Little I is getting bigger. Capital I is part of the input. It's not changing. It feels awfully like an exit condition, right? So that's why I stuck it up there, right? And then what does this one feel like? Well, S is our output, and little s keeps changing, but the goal is to find capital S and output it. So that feels like postcode to me. Right? People following this? Yeah? Well, are you talking about for the math or for the code? No, for the math. If you come back here, I mean, maybe this is all. I want this to be true. I know this is true. So how do I make this true? They got to be equal. Right? Right? Isn't that just, I don't know, that just seems straightforward to me. Right? Did I answer your question? Right? Yeah. 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 Well, I mean, we have a couple complaints about little s versus s. You know, capital S is the value we want to return, right? And I could have used capital S all the way through, but I wanted to sort of separate out the purposes of these things, right? Little s is the one that we're working through. We have the loop invariant, which tells us the relationship between these two, right? And then when we get to capital S, capital I, then we'll have our capital S value. Right? So that's the purpose. Now you might ask, why did I put it this way versus this way? Really, to mess with you. Right? The examples seem so easy that actually there are two reasons. The truth is when I was on the subway typing slides, I was in fact thinking, I need this to be this. So what do I need? I need the I to be I, and I need S to be S, and I wrote that down. Right? Because I wasn't thinking codes yet. I was thinking math. And then at some point I noticed, oh, look I put it the wrong way. And then I thought, hey, that's perfect. Because later we're going to be converting from math to code, and I want to feel that we're doing something. Right? And so when we're doing something, we're switching them. Right? This is a perfectly good math statement. So I can go, this true, this true, this is true. But then we can say it's not very good code. So here, what's the purpose of this slide? The purpose of this slide is we're focusing on what math do we need to get the proof to work, and then we're converting that math to code. And so, I don't know, this is the slides I came up with. Yeah? Yeah, they're equivalent. As a math statement, they're the same, right? You know it's true? I would say no. I would say at this point in the code, here, right, here, we know the value of little s, and in fact, capital S isn't even defined yet. We need to define it somewhere. In fact, we need to come up with what we're going to remember our post condition is that we find capital S and return it. So we don't have capital S. So if I tell you, right, you know little s, right? You don't know capital S. What code do you need to make little s equal capital S, right? Well, you make capital S equal little s, right? This is code, right? I'm putting code in blue. Yeah, right? This is a math statement. Right? Just like we were doing the difference between math and code before, right? This, I was focusing on what math do I need, and it doesn't matter which order you put it in, right? Here I'm saying I need to get the code which is going to make the math work, right? And given I don't know little s, and I do know little s, and I don't know big S, this is the obvious code to make this math true. Right? Maybe I should add in the slides here, right? I could put in here in green. Well, green is, maybe there's no difference actually between green and brown. There is, I don't know, but I got greens all the way through as my invariants and brown all the way through as my math. But really they're kind of the same. So here I could put in the assertion. I could put in the assertion, we need that S equals S, right? Little s equals s. And and what's my assertion here? Well, my assertion here is, well, we got the loop invariant, we know little s, we don't know big S, right? So how do I get from there to here? Well, I have to put some code. Right? Are we getting this? I really didn't think we were going to spend so much time on this. But it sounds like it was useful. Or was it useful because I made it worse, or did we make it better? Yeah?
I think only that part was confusing because people didn't know if it's an assertion or it's an assignment.
Right. Everybody good?